kinetic molecular theory and gases. We've discussed a bit of this before, but we're going to kind of put it together here in how we look at gases. So we have the kinetic molecular theory makes 5 assumptions, and anything that conforms perfectly to those 5 assumptions is called an ideal gas. Very few things in this life are ideal, and ideal gases don't really exist. It's just a simplified way to look at gases that make our calculations easier and faster without sacrificing too much in the way of accuracy. Now we have math that can actually get much more accurate, but at this level we don't have to. We can get close enough as long as if we think about these gases as functioning as ideal gases, but we do have to know their limitations. So the 5 assumptions and how we think of gases, the particle model here. They consist of large number of tiny particles that are far apart. Collisions between gas particles and between gas particles and the wall container walls are completely elastic. We assume that gas particles are in constant random motion and that there are no forces of attraction or repulsion between those gas particles. And the last assumption is the average kinetic energy depends on the temperature. Any gas that conforms perfectly to these 5 assumptions is considered that ideal gas, but nothing does. And really the sticking point is number 4. There's another one, but number 4 is the big one and the one I want you to focus on at this level. It says that there are no forces of attraction between gas particles. But there is a force of attraction that occurs with everything. London dispersion forces. Everything has those. Now, there are short-range forces of attraction. So if we get the particles far enough, they're not going to have that big of an effect, but they do exist and will affect those gas particles. And the other one is that a lot of times we see these gas particles as tiny, so tiny that the space that they themselves take up isn't significant and a significant amount of the total volume available. But as your container gets smaller and smaller, those tiny gas particles, or your concentration gets higher, then they're going to take up a higher and higher percentage of those gas of that volume. But the one we're going to focus on is that difference of the forces of attraction. So what I want you to remember about ideal gases isn't that they don't exist. What I want you to know are the differences between real gases and ideal gases. And we're going to describe those next. So deviations of real gases from ideal behavior. So how real gases are different from ideal. Well, gases have London dispersion forces at least. And so there are attractive forces. Now we can minimize those attractive forces by giving conditions of low pressure and high temperature. Now that's kind of hard to do because as pressure's low, we learned with Gay-Lussac's law that temperature should also be low. The way we solve this is with a giant container. If we have a big enough volume, then we can get our pressure low and our temperature high. We want our pressure low so that they're not banging on the gas on the walls of the container as much, which means there are very few particles in there, which means that their volume is negligible. They're only taking up a tiny, tiny little bit of that volume that is available. And temperature is high. This is a big one. So you got to remember pressure is low and temperature is high. When temperature is high, those gas particles are moving fast and they're going to be able to have enough energy to blow through any attractive forces that happen to form. So we want those particles moving really fast to make them behave more like ideal. Noble gases are close to ideal because they would only have those weak London dispersion forces, but nonpolar diatomic molecules are the closest, and probably those little ones like hydrogen gas. They're closest to ideal under low pressure and high temperature. The more polar a molecule, and remember if a molecule is polar, it can have dipole-dipole forces, which are quite a bit stronger than London dispersion forces. So the more polar molecule, the more attractive forces act upon it, and the more it's going to deviate from ideal behavior. So water vapor, think about it. It is polar and has hydrogen bonding, the strongest attractive force we have. So water vapor is nowhere near behaving like an ideal gas. All right, Now, like I said, we like to think of these ideal gases because it does make our math a little simpler without getting rid of any accuracy, or at least a whole lot of accuracy. So the ideal gas law is a relationship of pressure, volume, and temperature, and the amount of a gas. So that is one of the differences here from the combined gas law, is that this one also takes into account the number of moles of a gas. The ideal gas law looks like this. PV equals nRT. I'm going to call it per inert. Pressure is obviously P. V is volume of the container, and it is unit specific. It has to be in liters. T is temperature, and with all gas laws, temperature has to be in Kelvin. N is that amount of the gas, and it is the number of moles. All right. N is the number, put this in here, of moles. Now, you can be given moles and actually work through this, or what's probably going to happen, because things are measured in grams, is that you are going to get the amount of the gas in grams, and you would just have to convert that to moles using molar mass. R is the only thing we haven't talked about yet, and it is a constant. It's called the ideal gas constant, and it has one value, and that value will be given to you. But you'll notice here, there are three. The R is a constant, and it is one number, but because we can measure pressure in atmospheres, millimeters of mercury, or kilopascals, they went ahead and converted that one number for you. Now it kind of has crazy units, like this one right here is liter atmosphere per mole K. Those are just its units. It's just like writing kilograms, except longer. So you just plug those in there. And the only thing that is different are those pressure units. So look at pressure units to decide which R value to use.
Macy Boone, please come to the office. Macy Boone to the office.
If your pressure is in atmospheres, you're going to use this one. If your pressure is in millimeters of mercury, it's going to be this one. And if your pressure is in kilopascals, it's going to be this one. All right, so I have a little problem here that we can work. Go through and label your variables. A 2.07 liter cylinder, well, that's my volume. It is in liters, so that's fine, but it could be in milliliters, and you would have to know to change it to liters in order to get the correct answer. That cylinder contains 2.88 moles of helium gas. Moles, that is the amount of the gas, so that is in, and it does have to be in moles. Your degree C is your temperature, except that needs to be converted to Kelvin, so let's add 273 to it. It's 295 Kelvin. And we're looking for the pressure, so pressure equals question mark in atmospheres. So now we're going to work this problem. And so what we do is we've got all of our variables identified, and we need to decide which R value we're going to use. It is going to be this one right here, because they want the pressure in atmospheres. So I use the R value that has atmospheres in it. Then I need to rearrange my equation. So PV equals nRT. I'm going to solve for P. That means I divide both sides by V to get PV equals nRT, or P equals nRT over V. And then it's just plug and chug. N is the number of moles. My R value, I decided to use the 0.0821, and I put all those units in there. Then the temperature, 295, over my volume. Then watch your units cancel, and this is the last time to check and make sure that you've done everything correctly. So mole cancels with mole, liter cancels with liter, and Kelvin cancels with Kelvin. The only thing left not crossed off is atmospheres, and that is the correct unit for pressure. And when you calculate this, you need 3 sig figs, so 33.7 atmospheres. And that's how you work with the ideal gas